Okay, before we do a couple of operations, from the components of this vector, of course you know that these components make a right triangle, don't they? Which means that I could use the Pythagorean theorem to find the length of the vector, and I could use an arctangent to find the angle the vector makes with the positive x direction, say. Okay, well, we'll do that in a minute, but let me talk a little bit more about the notation. Okay, when I type a vector, I can't type it into columns because typewriters don't go in columns, and it's a lot of trouble to put things in columns. So I'm going to write a column this way. A semicolon means that this is a column. Semicolons separate columns. Okay, sometimes I'll write row vectors, and they're separated by commas. Although when we write them out on paper, we don't even put the comma in. But to distinguish a row from a column, I'll use a comma to make it a row and a semicolon to make it a column, and you'll see that shortly. So that's one possible notation. Another notation, it's equally valid, and you'll see this, and some authors use it, I use it sometimes. Now this is with a comma, and this is a less than sign, and this is a greater than sign, but we treat these as though they're braces. Pointy, I call them pointy braces, okay? Although on the typewriter I use the less than and greater than sign. In this context, these are called braces, pointy braces. Okay. Now let's talk about the length of the vector and the angle. Well, from the fact that you have Vy here and Vx here, and the fact that the x direction and y direction make a right angle, we see immediately that the magnitude of V, the length, or magnitude, and this is a lot like an absolute value sign, but there are two lines. So it's kind of like an absolute value sign with attitude, okay? The magnitude of the vector, designated with this notation, is just Vx squared plus Vy squared. Now there's another attribute of this vector, that's its direction. And, oh man, is there any color I haven't used here? Yeah, I've used yellow only briefly, so. Okay, now here's the x direction. So, this little segment's in the x direction. And here's the angle theta, the angle of the vector. And from simple right angle trigonometry, you know that the tangent of theta is, well, it's going to turn out that it's Vy over Vx. Now, how do I get that? Well, the way I've drawn this here, and this way is just coincidental, this angle and this angle are identical. Why? Because this is in the x direction, Vx is in the x direction, this is the x direction, so this and this are parallel, and this is just a traversal of a parallel, and you have alternate interior angles. Okay, in any case, the tangent of theta, the angle made with the x direction, is Vy over Vx So the angle is what? It's just the inverse tangent of Vy over Vx. Except that I want theta to uniquely define the direction of the vector. And that direction could be anywhere from the x-axis here all the way back around to the x-axis. The angle of this vector can be anything from 0 to 360 degrees. And if I don't have a 360 degree definition of this thing, I'm not uniquely, my angle won't uniquely define where the head of the arrow is, let's say. Won't uniquely define the direction of the vector. So, one problem with the inverse tangent, as I hope you know, and if you don't, be sure you review this, is that the inverse tangent is an angle between negative pi over 2 and pi over 2, or negative 90 degrees and 90 degrees. It doesn't go between 90 and 270 and negative angles and all that stuff, okay? So the way I designate this is plus 180 degrees if Vx is negative, and that takes care of it. And now theta is the angle, and you'll hear this again and again, theta is the angle of this vector as measured counterclockwise from the positive x direction. That defines the angle in terms of the components, and of course the components are easy to find in terms of the angle. And I can write that out, and that's really important. I'll write it in red. Vx equals magnitude of V times the cosine of theta, and Vy is the magnitude of V times the sine of theta, where theta is measured counterclockwise from the positive x direction. Now this and this tell you pretty much everything you need to know about vectors in 2 dimensions, or at least how to calculate the components, the length, and the relationship between the components and the length and everything. So this is very important. Now this is, again, foundational. We use this to build up much more machinery with vectors.